Hi everyone, my name is Aboritina Marion. We are a group of 4. We picked an interest in a machine learning domain that is assistive technology, and a project title is Reinforced Deep Q Learning for Sign Language Translation using Capsule Feature Extraction. Well, we all know sign language is a basic communication tool for people with hearing and speech disabilities, so whereby they have to focus on using their hand gestures, facial expressions, and body movements to put across what they're trying to mean. And this is not easy while communicating with the others, and it's a challenge because there are lack of interpreters or they are quite expensive, and hence they are faced with social isolation. So we plan on developing a real-time sign language translation system to bridge the communication gaps between the deaf community and the hearing world. This proposed solution is going to integrate ideas from computer vision and natural language processing to capture gestures from videos, translate those gestures into text using deep learning, and provide output in both text and audio. And this literature review shows us the current trends and how well the sign language translation systems stand globally. And the key advancements, the CNN-based systems achieved an accuracy of about 97%. So this gave us an idea to continue with this project and the relevance to our work. Our system focuses on using computer vision as well as the natural language processing. We also address the data scarcity with pre-processing techniques like resizing, normalization, and the argumentation. Then we have the problem statements. The problem statements are categorized into two. First, we have the domain application problems, mainly the challenges being faced. The deaf individuals face social isolation, the mental health issues, and barriers in education, employment. Then there is lack of tools to create the inclusive society for the streamless communication. Then we have the computational problems. These are basically the technical challenges. There is complexity, whereby there are varying hand shapes, there are continuous signs. Then we have the global variations. The gestures have different meanings across the communities, so it's hard to come across the data set that cut across. Then we have the data scarcity. Since this is an upcoming project, the specific data set that we plan on using is quite rare or scarce. I'm going to stop here. My other colleagues are going to continue from there. Thank you.
Hello everyone, my name is Nalwaga Joy and I'm going to continue from where my colleague stopped. Starting with a research question that says, how can a real-time sign language translation system leveraging or using computer vision, natural language processing, and advanced deep learning algorithms accurately interpret and translate sign language gestures into text and voice while integrating contextual understanding through a GPT mode? In regards or in relationship to this question, I'm going to start by talking about the objectives. Among the objectives of our work and research is to develop a real-time system that translates sign language gestures into text and voice using computer vision and natural language processing algorithms. Then another objective is to employ advanced deep learning models such as the convolutional neural networks for spatial feature extraction and long short-term memories for sequential analysis for accurate gesture recognition and translation. Then we also want to integrate a GPT for contextual translation and to enhance the accuracy and usability of the system. Then to also evaluate the system's performance by comparing it to other sign language translation models and measuring its real-time translation accuracy. Moving on, some of the research contributions of our work, we have been able to develop a real-time sign language translation system that integrates and interprets sign language using computer vision and natural language processing algorithms in order to convert the sign language gestures to text format or voice format. And this bridges the communication gap between the non the hearing community and the deaf community. Then we have built a system to combine convolutional neural networks for feature extraction and long short-term memory networks for sequential hand movements and analysis, hence ensuring accurate gesture recognition and translation. Moving on, we have implemented advanced models such as the capsule networks and vision transformers, as well as deep Q networks to improve the gesture recognition, hand tracking, the sign language translation, so as to achieve the purpose for which this feature or this system is being created for. Then we have evaluated the system's performance using different evaluation metrics, such as using the accuracy, the precision, the F1, the recall, in order to demonstrate its effectiveness in the real-time translation and superiority over other existing models. Then we have addressed the challenge of data scarcity by employing data augmentation, extracting frames, and synthetic data generation, hence enhancing the robustness and generalization of the system. This is the methodology of our system, and it shows how we are able to input videos, how the frames are able to be extracted, how we use the data sets and then it is trained, then how we use the capsule networks and the CNN models in order to extract features and in order to capture the different positions and poses, and then how we have been able to use the reinforced deep learning agent, and then how we are able to translate the sign language and then pass it through a GPT for text translation, and then the output will eventually be text or audio. Lastly, I'm going to be talking about the data set description, and part of the data set description as we enter into the exploratory data analysis graphs. The data set that we are using for our system or for our work is video based, and it's designed to recognize and analyze Ugandan sign language gestures. Hence, it captures the dynamic movement for both hands along with the detailed motion characteristics that are involved. And in our data set, we have the metadata that has the CSV data type that contains the data set crucial features such as the labels that are that are used for the sign language translations. Then the features of the dataset, we have the frames per video, we have the frame rate, we have the pixel intensity of the frames. This all is visual. This all helps in the visual capturing and the visual translation and the right capturing of the hand gestures and the movements. Then we have the left and hand right key points and the velocity or how fast the signer moves their hand as they are working out the sign language gesture, and then the labeling annotations that show the interpretation for each sign language. Thank you very much. I am going to hand over to my colleague to talk about the rest.
Hello, my name is Charlie Brian, and I'm here to take you through the graphical representation of data visualization and analysis in the datasets. So we begin with feature 1, which is the key point variability across all frames. Yes, and this focuses on tracking the general key point changes over a sequence of frames. Then the next figure, angle change over frames, demonstrates how an angle changes over a sequence of frames with significant fluctuations moving between 0 and 1 degrees. The next figure shows distribution of extracted features from the sign language video data. The next figure simply gives a sample of extracted frames from video 0.01. The next figure shows the shoulder key points over time. This simply tracks the position of a shoulder key point, and the Z coordinates show the most significant changes. The next figure shows the missing key points over frames, and the flat line at 0 simply indicates there are no missing points across all frames in the data set. Then velocity of wrist movement. We can see that the peaks in the graph simply indicate moments of rapid hand motion. Yes, and the next figure shows the key point, the post key point distribution, and this simply visualizes the locations of key points related to a pose that could be a central part of the body, leg, or even an elbow. The next figure shows the left versus right hand key points, and this is simply to analyze the dominant hand movements while signing. The next figure is the distribution of video lengths, which represents the frequency of videos placed within a specific frame, within a specific frame count ranges. Then key point clustering, the key points clustering. Each key point represents a point, and the colors represent cluster assignments from the K-means algorithm. Then the next figure shows feature correlations. It shows the feature correlations, and the diagonal values are 1.0 since each feature perfectly correlates with each other. The off diagonal values are close to 0, indicating little or no correlation between the feature pairs. And then moving on to the next, we have the histogram of key point positions. And then this simply shows that the distributions are relatively concentrated, suggesting that key points cluster in specific regions. Then the next figure simply shows the relationships and distributions among features, revealing their spread and range. Then moving on, we have the post key point clustering. where the cluster reflect distinct pose groupings or shared characteristics among pose key points. Next figure shows the distribution of average pixel intensities. Of course, as you can see, this box plot shows the overall image analysis based on the brightness or darkness of an image. Moving on, the three hand key point positions. Yes, the distribution of points suggests that clustering of key point the distribution of points suggests that there is a clustering of key points, and this simply shows that there are repeated hand movements while signing. Then the first key point density, it simply highlights the common facial motion areas in sign language video data. Yes, then moving on to the next, we have wrist velocity, wrist movement over time, and it visually represents the trajectory of wrist movement in the three-dimensional space. Then lastly, velocity over frames. Velocity fluctuates significantly, as you can see, and this indicates dynamic motion throughout the frames. Moving on to the last model selection, results, and evaluation. The CNN model with the 0.001 learning rate was chosen for deployment. This is because it's stable and accurate, and this is ideal for recognizing static gestures. The comparison of our results is as below, as you can see. Yes, and that's all I had to say. Thank you so much. My colleague will take you through the next part. Thank you.
Hello everyone, my name is Simon Abaho, and in this video I'm going to be taking you through the results of some of our model training. So first up is our results vision matrix from training the CNN model. As you can see here, true labels are plotted against the predicted labels, and this clearly shows that most of the labels here were predicted very well according to the scale here. As you can see, the 1.5 blue is a common square here, squares in the confusion matrix. Then we move on to the deep QN confusion matrix. Basically shows a concentrated area of 270, which means most of the models were highly predicted. Then the MLP confusion matrix, which is based on the Q learning confusion matrix, shows that here most of these labels that were predicted here are based on a gradient descent, and as you can see, so it's predicted. And then we have the MLP loss curve, training loss curve. Shows that the iterations or the epochs of the training increase, the loss of course decrease. Then we have limitations of this work. I think the major limitation was limited data sets we found in this region, in particular Uganda, because we have various sign languages in Uganda, which makes it very hard to overcome the data set. Then the models overfitting on the small data sets in this case, that was also another limitation. Then our requirements for high resources like GPU to process some of feature extractions of these models. Then the limitations of the research, basically this sign language in Uganda, in our project we're focusing on like one type of sign language, which means not scalable to other types of sign languages in Uganda, thus being limited to adapting to other languages. Then the real world deployment challenges, was the accuracy of the models. In this case also was high fact in this case. Then another thing is that most of the models were large in size, so which means it was very hard to like deploy them without first quantizing them and reducing them in size. Then we have bidirectional communication. In this case, for the start, our project is handling sign language translation to speech, but lacks speech to sign translation, which means it's not bidirectional. Then, as I had earlier talked about the sign language variation in Uganda. Most regions use different types of sign languages, which makes it very hard to come up with a model that can cater for all this. In future works, part of our next steps, also plan on making the bidirectional communication from speech to sign language translation, and vice versa from sign language to speech. Then also integrating these lightweight models in the edge devices like our smartphones, our wearable watches, and other real-time devices. Yeah, and also generating interactive learning applications to help people who are not aware of these sign languages. First, have like a brief overview teaching of how this sign language works. Then recommendations for further work include this might include collaborating with local dev communities to know how best to take on this project and exploring multimodal approaches like building a hybrid model combining the CNN, for example, with capsule feature networks, and also could use an advancement in the natural language processing like the GPT-4 to improve contextual understanding. Yes. Then acknowledgements. I'd like to acknowledge my fellow team members, Brian Atire, Tina Marion, and Joy Priscilla. Thank you.